My name is Peng. It's my pleasure to be invited by the conference to introduce our work. The title of our work is ScalaCache, Scalable User Space Page Cache Management with Software-Hardware Coordination. In this work, we found that due to the host-centric design principle, the existing page cache management suffers from CPU consumption, communication cost, and garbage collection interference. To address these challenges, we propose our software-hardware coordinated solution, ScalaCache. As background knowledge, I will briefly introduce the storage software stack, which is adopted in diverse computing domains like database and cloud computing. The stack includes two key components, Page Cache Manager and I/O Engine. The Cache Manager buffers the whole data in main memory to shorten I/O latency, while the I/O Engine concurrently accesses data residing in the SSD. Therefore, this component can narrow down performance gap between processors and the storage devices. One typical cache manager design is a Linux page cache, which implements page cache in the Linux kernel space. However, with the emergence of high bandwidth and low latency SSDs, many prior works note that the kernel stack fails to follow up on the SSD's performance boost. This is because the kernel implementation introduced heavy overheads such as global locking. To address the limitation of kernel implementation, recent works explore moving the storage stack into user space. The state-of-the-art design is tree cache. Tree cache employs the efficient user space SPDK I/O engine to accelerate I/O processing. Building a top SPDK tree cache customizes a lock-free page cache manager, where multiple threads are used for cache management, and the I/O requests are delivered between the manager threads and the application while message passing. We examine a macro benchmark to analyze the aforementioned cache designs and compare these designs with their ideal cases, which are estimated by scaling the bandwidth perfectly. The results show that this design inhibits poor scalability with the CPU costs. Specifically, kernel discrete performance by about 7% compared to the ideal case, while tree cache decreased the performance by 32%. They also cannot scale with SSDs, as evidenced by a 15.3% and 78% performance gap when utilizing 8 SSDs respectively. The root cause of the huge performance gap is the host-centric designs. That is, these cache managers exclusively reside on the host, overlooking storage taxes left by the host-centric design. The unilateral design imposes 3 sources of taxes, including CPU tax, communication tax, and the interference tax. First, let's analyze the CPU tax. The locking and the I/O engine in kernel page cache consumes 19% and 21% of the total CPU time respectively, indicating their huge CPU tax. As for tree cache, it dedicates multiple host CPU threads for each SSD to undertake cache management, reflecting its heavy weight. The CPU tax is exacerbated as the number of SSDs scales up. In summary, this cache management heavily taxes the host CPU resources, depriving applications of precious computing resources. Next is the issue of communication tax. The host-centric cache managers necessitate an I/O engine to communicate with SSDs. Unfortunately, the heavy I/O engine in kernel page cache impedes this communication. While tree cache adopted the efficient SPDK I/O engine, it allocates cache manager threads to communicate with both applications and SSDs. This tripartite structure prolongs the communication path. Our experiment shows that the queuing latency due to communication accounts for 78% of the total I/O latency. Finally, we discuss the interference tax. The host-centric designs cannot detect SSD internal activities, such as garbage collection, since multiple software layers of the storage stack sit between the host-centric manager and the SSD. Such software isolation leads to interference between the GC and the regular I/O requests, which compromise performance stability. To address these challenges, one of our key insights is the computational SSD. The emerging SSDs integrate powerful multi-core ARM processors and augment DRAM capacity. These substantial resources empower CSDs to efficiently process the offloaded task from the host. Another key insight is the host memory buffer feature in NVMe protocol, which allocates a DMA-able region in host memory to the SSD to buffer data. The HMB feature allows SSDs to directly manage data in main memory, while also ensures rapid data accessibility for applications. That is, this feature allows for SSD controlled page cache with the data cache on the host side. This key insight motivates us to offload cache management to the CSDs to address these storage taxes. To overcome these storage taxes, we propose two methods as our solution. We first offload cache management into CSDs to eliminate CPU tax. After offloading cache, we further coordinate software and hardware to overcome communication and interference taxes. This is our ScalaCache solution. First, let me introduce the architecture of ScalaCache. ScalaCache is a software-hardware coordination for user space cache manager, which achieves lightweight and scalable cache management with efficiency and stability. Specifically, we propose a high-performance cache index structure to enable lightweight cache management. Further, we design lockless cache management and the resources allocation framework within CSDs. These designs enable successful cache offloading, which removes host CPU reliance, that is the CPU tax. Meanwhile, we customize trimmed communication and GC-aware replacement to reduce communication and interference taxes, which achieves efficiency and stability. Next, let me introduce the design of ScalaCache. Let's start by talking about the design of cache management offloading. It's important to understand that we cannot simply offload the existing cache management directly into the CSD. As you can see in this figure, the problem is that the demands on computing power by existing cache far exceed what the CSD can provide. So what we need is a more lightweight cache design for successful offloading. Interestingly, we know that the FTL mapping table in CSDs and the cache index serve similar functions, which is to find the data location. Based on this observation, we propose the Fusion FTL, which consolidates these two indirection layers into a unified index structure. Thus, Fusion FTL can translate LPN to page frame or flash addresses based on a flag bit. By doing this, we simplify redundant address translation, making the cache lookup much more efficient. However, relying solely on lightweight cache management is insufficient since there are some potential bottlenecks inside the CSD. Multiple CSD cores may compete for critical resources such as Fusion FTL, free page frames, and flash throughout the entire I/O path, which result in performance bottleneck. To fully utilize each CSD core, we design a concurrent processing module within the CSD. We partition the address space, page frames, and flash evenly and bind them to each CSD core as its private resources. Based on the address space division, we split requests into multiple sub-requests, each handled by a different CSD core. By doing so, we can exploit each CSD core. Since each core manages private resources, these cores can access the resources without contention, which enable lock-free I/O processing. Thanks to our Fusion FTL and the concurrent I/O processing design, ScalaCache makes the cache manager lightweight enough to fit into the CSD. Therefore, the text host CPU resources are freed up for applications use, that is, removing the CPU text. After customizing a lightweight cache management inside the CSD, we come across another challenge, the overloading issue. Even with the improved management, the computing capability of a CSD is still limited. Processing all requests by the CSD leads to overloading issue, which significantly affects the performance. So to avoid the overloading issue and also shorten the heat path, we add a queue index within each client's thread. This queue index buffers page frame addresses to accelerate the cache lookup. This design balances the load between the host and the CSD, which fully utilizes the processing power of both sides. Next, we discuss how to reduce communication tax through the hardware and the software coordination. First, by offloading cache management, applications can directly access the cache and the flash within the CSD. This design transforms the tripartite communication architecture into bipartite communication, which trims the communication paths. Second, we also bundle multiple missing pages with discontinuous addresses into a single unmic command, which further reduces the communication overheads. Moreover, we reduce the GC interference through a GC-aware replacement strategy. We share the internal GC state to the host. After observing the CSD star GC, the host prioritizes the reclamation of clean pages when invicting page frames in the queue index. This is because invicting clean page frames doesn't require any writebacks, thus avoiding writebacks being blocked by the underlying GC. By designing these strategies, we successfully slash communication and interference taxes. After designing the hardware-software coordination for a single CSD, we next consider the multi-CSD scenario. To achieve this performance scalability across multiple CSDs, we design a parallel processing module that organizes multiple CSDs into a CSD array. This CSD array distributes error requests to different CSDs and leverages this CSD to handle requests concurrently. By doing so, we can aggregate computing power of multiple CSDs to deliver scalable performance. Next, I will show a part of our evaluation. We built our ScalaCache design on the family emulator. For evaluation platforms, we show the result of traditional Linux kernel page cache, the tree cache, which is the SOTA user space 1, the hardware, which simply offloads the cache management to the CSD, the ScalaCache, which is a software hardware coordinated user space cache manager that includes all our proposed design. We choose multi-block trees as our test workloads. We first compare the bandwidth of all platforms when using 8 host CPU cores. The overall result shows that ScalaCache outperforms all other designs in all workloads. ScalaCache outperforms kernel page cache by 5.12 times due to its lockless and user space design, while outperforms hardware platforms by 1.95 times as queue index accelerates cache lookup and avoids overloading the CSD. For tree cache, which employs 2 and 6 manager threads, ScalaCache outperforms them by 35% and 95% respectively. As ScalaCache frees up text the CPU for more client threads by manager offloading. ScalaCache also benefits from the lightweight design such as the Fusion FTL and concurrent error processing, which fully exploits the CSD computing capability. To show the benefit of the bipartite architecture, we relax the number of cores in tree cache. That is, it uses fixed 8 cores for client threads, while allocating extra cores as cache manager threads. Despite this, ScalaCache still outperforms tree cache. For example, ScalaCache outperforms tree cache, which employs 2 manager threads and 8 client threads by 29%. This is because more cache manager threads in tree cache increase the communication cost, limiting its performance improvement. In contrast, ScalaCache removes this communication cost. We can also compare the performance scalability against the varying CPU cores. The result shows that ScalaCache consistently shows improved scalability in all workloads. For example, the peak performance in SRC2 surpasses tree cache 2M by 36%. The good scalability is due to lightweight and lockless designs, including lightweight cache management, the lockless resource allocation framework, and the concurrent IO processing. We compare the tail latency between ScalaCache and tree cache into representative write-intensive workloads. Due to the GC-aware replacement policy, ScalaCache reduced the 99.99 latency by 11%. This reduction is unattainable with host-centric design manager designs like tree cache. To explore the effectiveness of this policy, we also evaluate the tail latency of ScalaCache with and without GC awareness. For example, the policy can reduce 99.9 latency by 17%. This result shows that this software-hardware coordinated fashion can alleviate GC impact by preventing GC from stalling dirty page writebacks. Finally, let me give you a conclusion. ScalaCache is motivated by the challenges that the host-centric cache manager incurs heavy storage taxes, including CPU, communication, and interference taxes. It's inspired by the key insight that we can offload the cache management and further coordinate the software and hardware. Thus, we propose our designs, including lightweight cache management in the SSD, trimmed communication, and GC avoidance, which successfully reduced these heavy storage taxes. About my presentation. Thank you for attending.